Good morning, everyone. Thank you for being here early this morning. I'll wait a little bit until a few more people come into the room. Okay, let's begin. Good morning and welcome to today's plenary session. My name is Carlos Portela, and today I have the distinct pleasure to introduce Professor Dennis Kochmann, a fantastic mentor and colleague who, among other topics, has made pioneering contributions to the realm of computational mechanics of architected materials, or mechanical metamaterials, over the last 15 years or so. Dennis is a full professor and head of the Department of Mechanical and Process Engineering at ETH Zurich. He received his diploma and Doctor of Engineering degrees in Mechanical Engineering from Ruhr University Bochum, and a master's degree in engineering mechanics from the University of Wisconsin-Madison. After a brief postdoctoral positions at the University of Wisconsin-Madison and the California Institute of Technology, he joined the faculty of Caltech's Aerospace Department, GALCIT, in 2011. In November of 2016, he became a professor of aerospace at Caltech, and in April of 2017, he joined his current institution, ETH Zurich, as a full professor of mechanics and materials. For his research, Dennis has received numerous awards, including the NSF Career Award, the Bureau Prize in Solid Mechanics by the International Union of Theoretical and Applied Mechanics, IUTM, the Richard von Mises Prize by the International Association of Applied Mathematics and Mechanics, GAM, the Thomas J.R. Hughes Young Investigator Award by the American Society of Mechanical Engineers, ASME, and the John R. Gears Award by the International Association of Computational Mechanics, among many other awards, including numerous teaching awards both at Caltech and ETH Zurich. He and his team combine theoretical, computational, and experimental techniques towards understanding the link between a material's microstructure and its macroscopic properties. The field of architected materials in particular has benefited from various of his team's contributions in recent years, some of which we'll hear about firsthand today. As metamaterial designs have increased in complexity, Dennis's computational contributions have provided efficient routes for their design and modeling, capturing complex responses ranging from failure, viscoelastic and viscoplastic responses, wave propagation, and nonlinear dynamics. More recently, his team has contributed pioneering data-driven methods for their inverse design and for predicting complex nonlinear responses. Without further ado, please join me in welcoming Professor Dennis Kochmann to the stage.
Thank you so much, Carlos, and thank you so much to the organizers. It's a tremendous pleasure and honor, probably a once-in-a-lifetime occasion once you hear me talk. And it's a great pleasure for me to talk about architected materials and computational mechanics. Thanks so much for coming this early. I know 8:30 is early in the morning. One of the benefits of coming from Europe is that you get up at 3, and at this time it's the middle of the day for you, and so hopefully I'll keep you entertained for the next 40 minutes or so. Why do we need computational mechanics for architected materials? I'd like to start with a brief history. Ever since the early days of humanity, we've tried to make materials that have the properties we want. And we've come a long way from the blacksmith and the alchemist in the Middle Ages to make materials that have the properties we need in engineering applications. Of course, we know how to process composites, how to process metals, how to process all kinds of materials. But about 30 years ago, there was an interest that came up in using structure to design materials with interesting properties. One of the early examples was the design of cellular structures that have a negative Poisson's ratio. Soon after, there was a lot of work in foams and lattices using structure to give interesting effective properties at the macroscopic material scale. And then something interesting happened, and that is manufacturing took over. Out of a sudden, advanced manufacturing and 3D printing enabled everyone to produce pretty much whatever structure you want. And now, out of a sudden, manufacturing was in the driver's seat to make interesting structures that buckle, that compress, that actuate, that do all kinds of things. Soon after, miniaturization set in. With the advent of two-photon lithography, you could make structures smaller and smaller. You could go to interesting new behavior, pentamode materials that behave like a fluid with almost no shear stiffness. You can make hierarchical structures. You can make structures across many different scales, designing them from nano to macro. And this continues until today. And so in this case, manufacturing has enabled our community of mechanics and materials to produce all kinds of interesting small-scale structures. Why does this matter? Well, if you think about classical materials, they get their properties from composition and microstructure, and we all know exactly how this works. And so if you test these materials, you get properties, stress-strain behavior, or effective elastic properties, elastic surface in different directions. And what we as engineers, as scientists, try to understand is the structure-property relationship. And this, many of us do on a daily basis. There's nothing fancy here. When you turn to architected materials, you introduce one more level. And this level in the middle has structure. And so this structure is literally a structure, which means if you zoom in, you find plates, beams, shells, something that we can describe with structural mechanics. And out of a sudden, the main relation that we're trying to understand is how to go from this structure to the macroscopic properties. Of course, the whole thing is still made out of an actual material by the end of the day. But once you know the base material properties, and these we can characterize relatively easily based on dog bone specimens, it's a structure that determines the ultimate properties. And this is what we're trying to understand. Of course, this happens not only at the smallest scale, you can also use this across scales. There are mattresses nowadays, there are fancy shoe soles, personal gear, bone implants, whatnot. All of these use structure to give you the properties that you need and you want in engineering applications. So why is this interesting for us as a computational mechanics community? Let's try to put the second C into the USNCCM, we're the computational mechanics crowd. On the one hand, there's a huge challenge that tries to understand what I call the forward challenge, which is, given a certain microstructure, what are the effective properties? And this is something we can try to cover and to cope with our classical computational techniques, trying to understand what the properties are. The second challenge goes the other way around. And the second challenge tries to understand the inverse, which means if you come to me with a certain set of properties that you want, or a combination of properties, how do we make structures that have exactly those properties? And I would argue the second challenge is even much harder than the first, and I will explain why. We as a computational mechanics community, of course, have a huge set of tools that we can use here, both for the forward and the inverse. And I'd like to talk in the next, 35 minutes or so about these two challenges. And I'll start with the forward challenge. Given a structure, what are the properties? Of course, this is not new. This is something we've been doing for decades, modeling structures, understanding properties. Sometimes it turns out that some of the techniques we have can actually be applied here much more efficiently than elsewhere. And I'll give you a simple example. Homogenization by Fe square has been around for since the beginning of the 2000s. And Fe square is something that's relatively simple. You solve a macroscale problem with finite elements, and whenever you need a constitutive response, you solve a nested microscale problem and you pass information back and forth. It's a great technique, but hardly anyone uses this. Why? Because it's extremely expensive. This is expensive from an execution point of view and also from a storage point of view. But if you talk about architected materials like these ones, it out of a sudden becomes feasible. On the macro scale, what we have is a macroscopic structure simulated by finite elements. On the small scale, I have a structure, which I can simulate, for example, by nonlinear beams. And now you can do Fe square, but the nice thing is down here, especially when considering periodicity, you have a very small number of degrees of freedom, and this makes it readily available. So what we do now is if the macro scale deforms, and this is described, for example, by a displacement field, and we also throw in a rotation field, I'll explain why in a second, you pass those and the gradients down to the small scale, you deform the unit cell accordingly, and then, using periodic boundary conditions, you figure out what is, for example, the strain energy density and elasticity. If it's inelastic, you use an incremental potential. We can differentiate this energy with respect to whatever we pass down. This we pass back as the stresses. We can even compute a consistent tangent. But this is feasible. It's relatively easy because the number of degrees of freedom on the small scale are so low compared to what we have if you mesh and actually solve an RVE. So this can be used instead of simulating a truss that has millions of beam elements and takes hours to compute on a server. You can run this in a few minutes on a laptop based on Fe square. And this works, of course, not just for show and tell, but this also works for actual problems. If you're designing impact-absorbing mats or shoe soles, you can run the experiment in this case, and you can beautifully compare the experiments to the homogenized Fe square simulation and the discrete calculation, and they match very nicely if you know the base material properties. So this is an approach where Fe square works very well. Of course, homogenization doesn't work everywhere. If you have the case of failure, of localization, of inelasticity, in these cases I cannot homogenize anymore, it just doesn't work. Another almost trivial example is fracture. Fracture mechanics is more than 100 years old, and we understand what happens. There's a stress concentration at the crack tip, there's a singularity typically. We've known this forever. But the moment that you put a discrete truss underneath, this doesn't work anymore, because now fracture toughness is not a continuum problem anymore. If you now apply loading remotely, and you look at the crack tip, you don't have a continuum. You don't have a singularity there because you have a discrete truss or frame. And now you have to look at which of these discrete structural members carries the maximum stress, and this determines fracture toughness. If you want to simulate this for huge systems, especially in 3D, this becomes insanely expensive because you have to apply your loading remotely. If only we had a technique that has full resolution somewhere, but then efficiently coarse grains elsewhere. And of course, here we can borrow from atomistics, for example. There's a technique called quasi-continuum, or QC, that was again developed more than 20 years ago to have full atomistic resolution where you need it, adaptively tracking down, for example, dislocation events, but efficiently coarse graining elsewhere to gain efficiency. In atomistics, let's be honest, this is a not widely used technique because it only works at low temperature, only for crystalline solids. It has a lot of limitations. But for trusses, this works beautifully. So what we do is we retain full resolution at the tip. We efficiently coarse grain in a concurrent multiscale setting elsewhere. Instead of atoms, we have our beam unit cells. And instead of interatomic forces, we now have the forces and moments that are acting between these beams. And now what you can do is you can coarse grain. So you have full resolution at the crack tip, and then you coarsen in many stages. At the crack tip, every unit cell retains its degrees of freedom, and as you coarsen away, you interpolate using methods of finite elements, all the degrees of freedom of a unit cell, and this allows you to tackle really large systems. Throw in adaptive remeshing. Our community knows how exactly this works. So here are two examples in 2D to begin. A simple Kagome lattice on the left, a triangular lattice on the right. The crack is where you can see it. If I now load this remotely and turn on adaptive remeshing, this is what happens. And you see one interesting thing, which is apparently the remeshing scheme in these two cases looks very, very different. Why is that? It's, of course, not an artifact. It's a feature. It's physics. Because if you zoom into the discrete solution, you look at the stress distribution, the stresses are distributed very differently based on architecture. And this shows that you can use the architecture and the design also to manufacture structures that have interesting fracture properties. So if you zoom in carefully, load is distributed very differently, and this gives rise to a vastly different fracture toughness of this compared to that, even though they have the same relative density, are easily manufacturable, and so forth. You can also compare this with literature, with experiments, and so forth, and we can see that with just a fraction of the degrees of freedom, we can capture the K1C fracture toughness, K2C fracture toughness, and you can even see more interesting physics. If you take the triangular lattice over here, a triangle is elastically isotropic. If you homogenize it, you get exactly the same modulus in every direction. But once you introduce a crack, that's not true anymore. Out of a sudden, it matters. What matters what exactly is the orientation of your crack relative to the orientation of the triangles. All of these things we can easily figure out with computational tools. Moreover, with this coarse graining, it even allows us to do this very efficiently. So you apply your loads very remotely, but you still have full resolution and the accuracy you need at the crack tip, simply by recycling the QC technique that's been around for 25 years or so. And with this, we can actually try to understand where the properties come from. We can go the forward challenge and go from structure to properties. You can do much more with this. I'll just give you one more example. Intertwined architected materials have become very popular in recent years. Carlos actually and team contributed to this quite a bit. And the idea here is that you don't rigidly connect structural elements, but you have loose contact between those. And this can be manufactured relatively easily if you have a multi-material printer. You simply print the ligaments, and you have a sacrificial material in between, which is resolved out. And then you have these loose contact elements. And if you engage them, for example, in mechanical loading, they engage in contact, they engage in friction. They can give rise to very interesting properties in terms of energy absorption, in terms of multi-stage deformation mechanisms, in terms of reorganization, reconfiguration, and whatnot. This is a computational challenge that we as a community can, of course, tackle to understand the effective properties. I don't want to talk much more about this, so I don't steal Elias Spatiali's thunder. He's talking about this on Thursday. If you're interested, feel free to attend his presentation as well. So far, I've been talking a lot about modeling these architected materials. And this really is the forward challenge. And as I said in the beginning, I claim that this forward challenge is much easier than the inverse challenge. Why is that? I would say it's the case for two reasons. Number one, if you want to tackle the inverse challenge, you first of all have to have a good forward model. And this I try to convey we have as a community. We have the tools to simulate these structures. But the second problem is a more fundamental one, and that is the inverse problem is inherently ill-posed. If you come to me with a structure, I can uniquely figure out the properties. Of course, there's some uncertainty possibly, but you perform an experiment, you perform a simulation, you know the properties. If you come to me and you say, I want a structure that has certain properties, I can come back and give you a myriad of structures that all have the same properties. Which one do I pick? It's an ill-posed problem because there are many solutions to the given challenge that you're posing. Of course, there are fantastic techniques to deal with this inverse challenge. One of them is topology optimization. It's a great tool. It will be a great tool. It will not be replaced, don't get me wrong. But even topology optimization, to some extent, depends on a good initial guess, because you're looking for a minimum in a multi-objective landscape. Of course, we have some of the experts in the audience on topology optimization. What I would love to have is inverse design methods that are generative in the sense that they don't rely on a good initial guess. They don't rely on intuition or experience of the user, and that still try to explore the vast design space to give you the properties you want. How do we do this? Let me start with a very simple example. What you see here are truss lattice unit cells. If I populate them periodically in space, this is a lattice, and I can homogenize this. I can, for example, figure out the effective stiffness. This is nothing else but the stiffness surface, which shows you Young's modulus in all directions in 3D. So this is the homogenization step, which is trivial. Anyone who can use Abacus or Phoenix or whatever can do this in a millisecond. I mean, computation time. The coding takes longer. The inverse challenge is harder. If you come to me and I say, I want a material that has exactly these properties, what is the structure? And this is the challenge I was talking about. There's not just one, there are many structures that may have exactly those properties, and this makes it harder. Of course, what you could do is you could generate a lookup table. This was a nice study, coincidentally, from ETH colleagues who took more than 10,000 naturally occurring structures, and they homogenized all of them. Then you create a gigantic lookup table of their anisotropic Young's moduli, shear moduli, and so forth. And now you have a database to consult. It's like in the old days, when we need a material, you go to a lookup table. You find the one that has your preferred properties, and you pick that one. But this has challenges too. So let's say you have an actual application. I was talking about bone implants in the beginning. And let's say you want to design a bone implant. So locally, you maybe know what the effective stiffness is based on properties of a human bone. But if you use a lookup table, there are a few challenges. First of all, your lookup table is limited, again, by your intuition and experience, because you started with 10,000 structures. What if you need something that's not contained in that set? And bone implants are a very hard challenge because no two bones are alike. If you poke a bone and you figure out what is the effective 3D stiffness, on two different spots in the same bone, you get different properties, and then if you go from patient to patient, it's even worse. So you really need a vast property space here. And it would be great if we had a technique that told us on the spot what certain properties are, so we can look at the vast space of relative densities, of stiffnesses that you actually find in human bone. And now, in the age of AI, why don't we go to GPT? It usually asks, how can I help you today? Let's say we type in, can you identify optimal metamaterial architectures for this application? And wouldn't it be nice if GPT answers, of course, here you go. And it produces structures. This, of course, is a dream, or it was a dream, because in reality, this doesn't work. Note that, of course, GPT should not know that you're talking about trusses or shells. It should just give you optimal designs. And what exactly those are is up to the framework to figure out. Why am I showing you this? The reason is we're actually going to use AI to solve this challenge. Everyone knows that AI can also generate images. So here I went to GPT, last week actually, and I just typed in, give me a photo of 4 engineering professors solving a hard computational mechanics problem. That's what it produces. The text in the background is gibberish. It doesn't make any sense. See if you recognize yourself here. The main point is these 4 characters don't exist. They're fictitious. It's generative AI, but this is what AI, the well-trained AI, believes the engineering professors look like. Nice. We can do more than this. About 2 years ago, Sora came out, and Sora is a video generation tool. In this case, the prompt that was used is a drone camera circles around a beautiful historic church built on the rocky outcroppings of the Italian Amalfi Coast, blah, blah, blah. And it generates this. This village doesn't exist. This footage doesn't exist. It's not a video search online. This is generative AI, meaning this is what the model believes the Italian Amalfi Coast looks like. If you look at the video very carefully, you'll notice that it's fake, because there are many instances in which we find hallucinations. It starts again. Please just have a look at the people walking down the stair in about 3 seconds or so. And you will notice that these people, for example, it's a hallucination. It's obviously fake. This doesn't exist. It doesn't really help me find a specific place on the Amalfi Coast, but it gives me a fantastic impression of what the Italian Amalfi Coast looks like. So I have, without intuition, a good idea of what it looks like there. Again, where am I showing you this? Or let's start like this. How does this work? These diffusion models that are behind the image and video processing work on a relatively simple approach. You start with actual images, of which we can find millions online, and you gradually diffuse those. That's a forward diffusion process by adding Gaussian noise until you successively, at the end, arrive at true Gaussian noise. Now, what we have to learn is the reverse process, which is known as the denoising process. You basically go through a Markov chain in reverse. And if you want to generate an image, you have to provide a prompt. And we have these prompts because every image that you can find online typically comes with a description. Here it's a white cat with gray hair lying on the ground or whatnot. What we have to do now is train this reverse process with the prompt so that you get out what you have in the beginning. These techniques have been around for a while. This is based on 3D UNets that came out of Freiburg in Germany originally, and it does this diffusion process very effectively. So just to give you an idea, what it means is you take images, like this guy up here, you successively add random noise, and then when you go and you prompt, I want a handsome and smart mechanics professor, you have no control over what you're getting, because the thing just produces something that is a handsome and smart mechanics professor. Sorry, Carlos. But it gives you something that satisfies your prompt, but it doesn't have to necessarily be something that is either real or is what you're looking for. Again, why am I telling you this? Wouldn't it be nice if I put in the prompt, let's create a video showing the finite element simulation of a periodic unit cell having this stress-strain response and compression? And what I want is something like this to come out. I want a video that shows me the compressive response, for example, with the compressive stress highlighted in color code. And this satisfies, basically kills two birds with one stone. On the one hand, I get the simulation for free, but it also shows me the structure. And that's what I wanted in the beginning. I want a generative design that tells me a structure without guessing or intuition that has exactly the response that we want. Does this work? Well, we can use the original scheme. Every video has RGB channels, red, green, and blue. We override those with the horizontal and vertical displacement components and the stress in the vertical direction, because that's what we care about. And we can even build in physics, which is very important here. For example, I know that the sum of all sigma vertical components in any row must match the effective response, because this is the homogenized response. I also know, if this is quasi-static, that the sum of all the vertical stresses at every single row must be the same. So I can build in physical constraints. It's not just random video generation like online, where a person can have 6 hands and 3 eyes. Here I can build in physics, and this allows me to work with much smaller data sets than what we can do online. So now we need a data set. Here we tried something simple. We use Gaussian random fields to generate these random structures. We do a thresholding to figure out solid and void. And we mirror it twice to make them periodic. This is a 2D example. And then we simulate those. And the simulation, we tried to make it as complicated as we can. This is an elastoplastic base material, including plasticity and failure, calibrated by 3D experiments, by 3D printed experiments. We introduce contact and friction, and then we simulate about 53,000 of these structures. And for each of those, for every structure, we obtain a video showing the response with a color code highlighting, for example, the stresses, and we get the effective stress-strain response. What we want now is to go the other way around. To this end, we have to somehow parameterize the stress-strain curve. For example, you can pick equal strain increments and just record the stress values. And once you have these stress values, what I want is, this is now my prompt. I pass this to the diffusion model, and what I want to get out is the structure on the left. That's exactly what I would like to do. So we tried this, and it turned out it works amazingly well, just with 53,000 structures. So here's an example. The red dots are the stress-strain response that we wanted. We wanted to make it challenging by having something that's first soft, and then it hardens dramatically. If you look through the 53,000 samples in the training set, the white line is the best match we could find. If we use the diffusion model, it shows us this structure and this video, and it tells us that the stress-strain response is the green over here. Now, we can't really trust this, but we can take the structure, put it into a finite element software, and see what it really is. And what we get is the blue line in the simulation on the right. And if you look at the stress-strain distributions and the curve over here, they match beautifully exactly what we wanted. We didn't do this just for one curve. We did this for thousands of curves and also reported the average errors and maxima. And what you notice is that this really generates interesting structures. In this case, for example, this is what the 3 best matches in the training data set look like. This up here is the structure we generate. So it really does not just interpolate between 2 nearby structures. It generates something new that was not contained in the training set without intuition or experience. Here's another example with pronounced softening. Again, it spits out the structure. This is the FE calculation of ours. This is the diffusion model prediction. It has exactly more or less the stress-strain response we want. What's interesting is in this buckling problem, this column can either buckle left or right. And so in principle, in the generated video, it could jump left and right and do funny things because it doesn't know the physics, but still it gets it right? So you really get a response that makes sense. One point I would like to make is about extrapolation versus interpolation. Of course, this is only interpolating in the design space. Here we used pixels to represent the video. We have about 100 by 100 pixels, and we must interpolate there. We just put pixels in different positions. But that does not mean that we also have to interpolate in the property space, because we can design structures that have properties far outside what we had in the training set. Here, for example, what you see in gray are all the different curves that were contained in the training set. If you now say, give me a structure that is 20% stiffer than the stiffest structure you've ever seen, it can easily do this. If you go to the opposite end and we say, give us a structure that is 20% softer than the softest structure you've ever seen, so if you notice the scale, this is really down here at the bottom, it can also do this. And so, yes, we're interpolating in the design space because we're fixed to our pixel grid, but we can vastly extrapolate in the property space, and that's very interesting. You can generate structures with properties you have not seen before. And this can be extended in many ways. So what we're doing now is we use pixel data to predict the structures. In principle, you don't have to use pixel data. If you like trusses, you could do a similar thing with a truss. In this case, we use a graph representation. Here, the node positions and the connectivity information between nodes is what we care about. What we're doing now, by the way, this preprint was just published last night, I think, if you're interested. What has become very popular in recent years are these implicit equations, so triply periodic surfaces. What's nice about those is you can represent them very easily by one single implicit equation. All you have to do is put together a few cosines and sines. You set this to 0, and the leveled set of this gives you exactly those shell structures. And they're used in many applications nowadays. Now, of course, this is not pixels. This is an equation. Can we learn equations? Turns out we can. All you have to do is turn the equation down here somehow into a vector similar to pixels that can be learned. What we do here is we use an algebraic language approach. We basically dissect the equation. Every number, every comma, every plus, every minus, every cosine and sine is like a word in our vocabulary. Each one of those is assigned a number, and based on this, we can easily translate any equation you want into a vector of numbers. If you use a careful embedding, you can make sure that this adheres to algebraic correctness. So cosine plus sine is the same as sine plus cosine. It must know this. But we can use this to translate any equation into a vector similar to pixels. And now we're in business again. We can give it a stress-strain curve, and now we want an equation to get out, which tells us what the structure looks like. We can do even more. This is a single objective stress-strain response. What if I say, in addition, I also want to optimize, for example, the 3D anisotropic stiffness? Now it becomes a multi-objective optimization. These things we can do with the tools. I'll just show you a few examples. Here, we really wanted to go to town and design a curve in blue that kind of doesn't make sense. It goes up and down all the time. If we take the top 30 picks from our training set, they're all over the place in white. The best match, according to mean squared error, is the yellow one. But if you use the diffusion model, this is what comes out. It gives you an implicit equation, which, if you compress with finite elements, gives you the blue curve that runs almost exactly through the points you want. This is strongly nonlinear, of course. Like I said, you can also do multi-objective optimization. So let's say I come and I say I want a stress-strain curve that looks like this. The best match in the training set is actually fairly close. But let's say we want a second objective. I want the structure to have a very particular Poisson's ratio so that it deforms in a certain way in the transverse directions. If I look at the best match from the training set that has a Poisson's ratio close to 0, let's throw in a second target, and let's say I want 3 different structures. They're all supposed to have this stress-strain curve. One of them is supposed to be very auxetic, having a negative Poisson's ratio of -3, one close to 0, and one close to 1. Keep in mind this is anisotropic, so the classical bounds don't apply here. If you run it through the diffusion network, what you get is this. You get 3 different structures, and each of these designs 1, 2, and 3 matches the nonlinear response that you wanted, based on buckling and compression. But each of those has a fairly distinct Poisson's ratio of -3, close to 0, and close to 1. We can use this to not only get the nonlinear response, but we can also use this to get the kinematics we want, so that it either enlarges in the lateral direction or it shrinks, or vice versa. And this is of great interest if you're designing, for example, shoe soles or mattresses or things like this, where you care both about the compressive response and also the kinematics of deformation. And of course, we can also do this in experiments. Up here you see 3 images. Li Zheng, a PhD student of mine, printed a whole bunch of structures and then tested them with an instron. And we found that these predictions match very, very well. If you'd like to find out more, the paper's on the archive now. I just want to show you one more example here. I mentioned the bone implants in the beginning. For bone implants, we really don't care so much about nonlinear stress-strain response. Ideally, we should never go into that regime upon loading. But we care a lot about the correct anisotropic stiffness. And for many bone examples, folks in biomechanics have characterized the anisotropic stiffness. And here are 2 examples. This is actual trabecular bone from a cow. This is what the 3D stiffness surfaces look like. And now I use this as the input, and I generate structures that have exactly this anisotropic behavior. Here you get 2 on the left, you get 2 on the right. And so that it's not eyeballing, I'm also showing you the 3 cross-sections through the elastic surface. And they match the target super well. What's nice is, because this is a generative AI tool, it generates not just one structure, but as many as you wish. You repeat the algorithm 10 times, and you possibly get up to 10 different structures. And then you can build in secondary constraints. Which of these 10 are easiest to produce, to manufacture, to test, whatnot. And so it really is a rich tool. If you're very careful about the design, you can also design the unit cell so that you can spatially grade. Let's say you know it's optimal structure 1 over here, optimal structure 2 over there. How do I connect those? If you're careful with your design, you can spatially grade. So you actually have one structure on the left, one structure on the right, and you have a smooth transition from one to the other. And these spatially graded structures are of great interest because typically in applications, you don't just want one property, but you need different properties in different spots, as I was saying at the beginning, and this way you can grade. You can even do this more complicated, but I don't have time to talk about this. You could use this as the input for multiscale topology optimization. You're trying to optimize on the macro scale. On the micro scale, you then use your optimizer to figure out what the optimal properties and the optimal structures are locally. All right, so this spatial grading has one other interesting feature. And this is the last example I'd like to show you. AI is a fantastic tool if trained well and dealt with carefully, but it's not the ultima ratio everywhere. In some applications, we can still use good old optimization, and it actually turns out to be very powerful. And I'd like to show you one example of spatially graded structures that we've been working on recently. So far, everything I showed you was static or quasi-static. We slowly load them, we figure out effective properties. What if we look at waves? The story becomes more complicated because now we have dynamic properties. Imagine you make a spatially graded structure, such as the one we see over here. And in this case, the unit cell changes from point to point smoothly. But let's try and make structures like this that allow us to guide waves in ways that we want. Here I picked a very simple design. If you look carefully, you will figure out that the unit cell can be described by only a single design parameter. If this is the unit cell, the white guys are beams. This is 2D. And my design parameter theta simply tells you where this point over here is. For a small theta, you basically have a little square in here. For an increasing theta, this becomes a star. And now I just have one design parameter theta that varies through space. And the question is, how do I arrange this in space? And the challenge really is, how do I model this if I'm dealing with millions of unit cells? And how do I do dynamic optimization? So here, we turned to actually optics, and we adopted a technique that's used there. We cannot really use transient FE calculations because it becomes a mess to optimize the dynamic response. How do you optimize wave motion using FE? What we do here is the following. We still treat this as a somewhat homogenization problem. We assume that locally you still have a periodic medium, but that this smoothly changes from one point to the other. At every point you can still homogenize, but this is changing as you move through the lattice. In dynamics, we cannot just homogenize stiffness and density. What we typically look at are the so-called dispersion relations that tell us if you have a wave with a certain wave vector k, at what frequency does the wave propagate. And this we can determine from homogenization. It's a computational technique that every FE code can easily do nowadays. You can do this for every single point inside your medium. If I don't want to use FE, what then? We use something that's known as ray tracing and has been used in optics for a long time. We use this for dispersive metamaterials. And the idea is that you start at a certain point of excitation where you excite your lattice, and now you shoot a ray. And now you have to figure out where this ray is moving. And for this, we have a system of equations. We have one equation that tells us the path of this ray, and this has to do with the fact how these dispersion relations change locally. We also have an equation that tells us how the wave vector changes as you navigate through the medium. And if you consider small vibrations, the frequency is fixed. It's the one that you use as a target frequency for optimization. Speaking of optimization, Now, we shoot not just one ray, but we shoot many rays. If you excite at a certain point, waves will go everywhere. So we shoot a whole bunch of rays into space, we solve the equations, and we formulate a design optimization problem. And the idea here is, let's try to figure out my design parameter theta everywhere in space. I can interpolate it using finite elements, for example, such that I define a priori where these rays are going to end up. Let's say I excite the structure here. I want all the rays to go through a certain point. This would be focusing. Or I want them to fan out. This would be lensing. I want them to turn around a corner. I can formulate this as an optimization problem where I try to bend the rays in ways I want, subject to the ray tracing equations. And this can be done fairly efficiently with adjoint-based optimization techniques. So here's one example. Let's say you have your design domain. This is what my unit cell looks like. We excite this at the center, and I want to make sure that all the rays exit perpendicular to the 4 boundaries. I run the optimization, and this is what my design parameter distribution theta looks like. If you look at the rays, what this means is you excite it at the center, and the rays all go perpendicular to the boundary out of the 4 sides of the thing. And if you look in the back, you can even see the unit cells. They have very small theta here, and they have the star-shaped large theta in the other regions. You can do something else. Let's say I want a plane wave to come in from the left, and I want it to be redirected, so it exits as a plane wave at the bottom. This is what theta looks like in this case. On the right, you can see what the actual structure looks like, and this is what the rays look like. Why am I doing all this? Well, now let's play puzzle. Let's say I take the first tile, I excite at the center, now my rays go out to the side, perpendicular. Let's put the next tile next to it, which means now the rays are being redirected by 90 degrees. Let's put another tile below it. And so by doing this, you can really guide something relatively simple that directs your waves in arbitrary ways you want in 2D. If you now excite the whole thing, your wave can go in whichever way you prescribe. And this is of great interest for energy harvesting, for vibration insulation, for signal processing, all these things, that, particularly in MEMS and NEMS devices, we need. All based on simple adjoint-based optimization. And this is not just a dream, so if you now run an actual transient FE calculation, you excite at the center at your design frequency, you will find that the waves actually move in what we call a figure 8 design, right? They just bend around, nothing reaches the top right and bottom left corner, they just keep going in the figure 8 design. And you can really play puzzle with this. You can make this as complicated as you wish. Luckily, we also figured out a way to make those. So more recently, we've been using wafer-type fabrication techniques. In this case, all you do is you take a thin wafer, you pattern a structure into this. Because you use silicon wafers, this has pretty much no damping. Waves will go forever. We can make unit cells as small as a few microns. In this case, we can fit millions of unit cells onto a 2D wafer, and you can really print those designs that I just showed you, where your unit cell changes from one point to the other. And with this, we can build, we can test. This is the setup from our lab, where the sample is here in the middle. It's basically a thin silicon sheet, which you excite from below with a laser. And then we look at it with an interferometer from the top, which figures out the displacement, the out-of-plane displacement. And if this is the figure 8 that we simulated in the beginning, we can now do line scans. If you go around along line L1, you'll see that the wave spreads exactly until it hits this point up here, and then the wave disappears because it turns by 90 degrees. If you go along line L2, you'll figure out that nothing happens until the first wave hits here, and then the second one hits there. At L3, you see the wave arrive after a while and then keep going. So we can really scan the full space and figure out that the wave is going exactly along the range we want. You can do this much more complicated, of course. You can do different designs. Here are just some examples of how you can put the tiles together. We also realized that this works not just at a fixed design frequency. We can do this over hundreds of kilohertz. It still works. And this opens up new opportunities for making structures that direct waves wherever you'd like, that have signal processing capability. We can make some of the low-frequency waves go left, high frequencies go right, and all these kind of things. What I really like about this example is we've put computational mechanics back in the driver's seat. Because as I said in the beginning, manufacturing had more or less taken over, and you can make all of these small-scale structures nowadays. But now that we can do this, and everyone has the capabilities almost to fabricate these structures, computational mechanics really is getting more and more importance, because now the question is, what the heck do we fabricate? Right? It shouldn't be trial and error. It should be simulation, guided design, and optimization. And that's exactly why computational mechanics is definitely back on the table and in the driver's seat. Since time is running out, let me quickly summarize my takeaway messages. First of all, multiscale modeling and design optimization of architected materials is a very interesting, or are very interesting computational challenges that many should look into. There's a huge design space, there's a huge property space that can be explored. I just showed you the tip of the iceberg. There's so much more one can do. These AI-based approaches that I showed you offer interesting alternatives, both in modeling and design, but my take is that we should combine them with physics and science. Just AI is one thing, but if you can build in the physics and the scientific principles, they're much more powerful. And the last point, there's so much to do. I only talked about going from the middle scale to the macro scale. I completely glanced out that there's also a material scale. And we can leverage this as well. This is where small-scale fabrication really comes in and gains importance. There's actuation techniques, there's multiphysics, all the things we're hearing about in the many sessions today, all of this can be applied here as well. Anything you can fabricate, we'd have to somehow design and optimize, and this is where computation comes in. And with this, I'm literally at the end. I thank you very much for your attention. I'll be happy to take questions or comments. Thank you.
Thank you very much, Dennis. I think I finally understood your diffusion models. All it took was one example. Thank you. Thank you very much. So we have a few minutes for questions. So we have someone with a microphone on the floor. So
don't be shy.
There we go. Yes,
so
please
thank you for your nice talk.
Thanks.
You have talked about the acoustic wave in the metamaterials.
Yes.
Could you comment on the failure patterns?
Failure.
The metamaterials
Yes.
against impact loading, mechanical impact.
That's a very interesting point. Actually, Carlos is the expert. He's doing small-scale impact into metamaterials. It's a very interesting challenge. So fracture is one thing, failure. We've actually looked at optimizing fracture path in disordered solids. There's one thing you can do. Impact in particular gets interesting because at these small scales, the time scale of impact and the time scale of wave motion become commensurate at some point. And then you can really play with what I was saying on the previous scale, on the previous slide. You can really play with the interplay of structure and actual wave motion inside the solid. I think there's still a lot to do. There are some initial experiments. Carlos and company at MIT did some really interesting experiments of shooting small-scale spheres into these architected materials. But I think it's far from being understood from a theoretical computational perspective. Did that answer your question? Thanks.
We have a question right here in the front. There's the microphone.
Thank you, nice presentation. I do have a question. Considering the size and scale dependency of the fracture and failure, how do you overcome this millions of billions of elements to unlock the fracture and failure for the material design in artificial materials?
So when it comes to fracture, what we particularly do is we use multiscale techniques that have full resolution at the crack and try to be efficient elsewhere. This is what I was trying to show with the QC-based fracture simulations, where you really need full resolution only at the crack tip or in the vicinity of the crack tip, but elsewhere you don't. And so if you have a good adaptive remeshing scheme, then you can still simulate failure and fracture, but only resolving the regions of interest. Did I understand your question?
Okay, thank you.
Sure.
We have time for another question right there in the back. Middle back.
Just scream.
Thank you very much for the presentation. I have one question regarding the metamaterial prompting there. Have you thought of adding manufacturing constraints like minimum feature size and stuff?
Yes. So honestly, if you're interested in this, you should really go to Jamie Guest's talk tomorrow. He's talking about topology optimization with fabrication constraints. But yes, so one of the things there are two things we can do. The one is we can actually build constraints into the optimization. In fact, that's what we do. We limit, for example, the feature size. We don't want the beams to be infinitely thinner. So this we can easily build in. That's one thing we can do. The second is generative design typically gives you very many different structures that have similar properties. And so then you could also, in a heuristic way, apply secondary criteria afterwards. You just look at the 10 structures you have and see which of those can I print on the one specific printer I have in the basement or so. But these two approaches can be readily applied, yes. It's a good point.
Okay, we can do one last question here in the front. Yes.
Hi, Dennis. Fascinating talk.
Thank you.
And thanks for putting computational mechanics on the driver's seat. Dennis, the question I have for you is the one that you alluded to in the beginning of your talk. How do you know that all your AI models are not hallucinating, especially for the type of problems that you are solving,
Yes.
especially when new physics come on, and so on, and especially considering
Yes.
the evolution of these models?
This is a great question. Thank you for asking it. In fact, they do hallucinate. I missed to say this in the interest of time, I think. But if you look at, for example, these structures over here very carefully, if you look at the video on the left, you will see that in certain instances, they're not even connected. There are pixels missing. And this clearly is a hallucination. That's exactly why I need the post-processing step of doing an actual cleaning up. So this is what I meant by, don't get me wrong, I'm not saying this is going to replace topology optimization. No. It just gives you an initial guess from which you can start, and then you could run topology optimization to give you a structure, right? It just gives you initial guesses. This is not the perfect structure by all means. So anyone who does top opt, you're not going to be out of job for a long time, I think.
Amazing.
Thanks.
Okay. On that note, in the interest of time, I think we'll wrap it up here. And please join me in thanking Dennis one more time.
No, thank you.